All right, so last time we had started section 2.2 and we talked about Venn diagrams, just briefly. We had drawn this particular picture, and the part inside of the circle A was called the set, and then the pink part on the outside, but still inside the square, was called the complement of the set. And we had seen this definition for complement. It's everything that's inside of the universal set U, but it's not inside of circle A. That's what complement means. So we're going to continue with that idea and do an actual example now where we're given numerical values. They don't have to be numbers. They could have been letters. They could have been people's names. It doesn't matter what they are. But we have elements in a set that are given for our universal set. And then we're given a created set. We'll call it A just so that we have the ability to use a little bit of notation. So we're going to call this thing set A. All right? And what we're going to do is we're going to find the complement of A. So the notation for complement of A is this sort of accent mark on A. It's not the only notation that exists for complements. If you've seen another book somewhere along the way, sometimes another complement will be an A with a little C, kind of as a superscript. And sometimes you'll see an A with a bar on top. So in my elementary math classes I teach for like elementary ed majors, this is the notation that our book uses, is the second one there. Okay, so they're just used interchangeably. So for ours, we're going to use the accent mark. So A complement means everything that's in the universal set, and our universal set is the numbers 1 through 10, but is not in set A, which is 1, 2, 3, 4, 7, 10. So what elements, in other words, are sort of left out of the description of A? 5, 6, 8, and 9. Is that okay? All right. So we're just finding the missing pieces. Now, this one right here is a little more odd looking, perhaps. It actually says the universal set. Well, I need everything that's in the universal set that's not in the universal set, and that would be nothing, right? There's nothing that fits that description. So this is actually, if we do the universal set complement, it's actually the empty set like this. The set that has nothing in it. And we talked about that back in section 2.1. So it's actually very interesting because the universal set's complement is the empty set. And if we'd asked sort of like maybe question 2A or 2B down here at the bottom when we said, what's the complement of the empty set? Well, the complement of the empty set would be the universal set. So they are each other's complements. They go back and forth. Okay, so we have a set A, and we actually have the ability to break the set down even more. And when we do that, it's called a subset. So if we have set A and B, A is a subset of B if every element of A is also an element of B. And it has this notation that looks kind of like a less than or equal to sign, except that it's curved. Right? That's kind of what it looks like. And that's actually a really nice notation to sort of keep in your mind that this kind of looks like less than or equal to, because it has the same sort of feel to it. Right? It means that it's smaller or equal to the set we're talking about. In terms of a picture, if I were to draw a Venn diagram, what this looks like is concentric circles. So if A is a subset of B, it means A is inside of B. Does it look like A is smaller than B, picture-wise? Yeah. So that sort of idea of feeling like it's smaller than or less than is sort of verbally, that picture is true. The one condition is that like line on the bottom of it means they could be equal to one another. Just like less than or equal to could be equal to one another. So when we see this line on the bottom of them, we would actually say that A is also a subset of itself because it's equal to itself. Or B is a subset of itself because it's equal to itself. So that line on the bottom means or equal to in some kind of a sense. So this is what subsets would look like. We saw a definition of set equality last time. Set equality definition talked about the elements of set A and the elements of set B being the exact same group of elements. And I gave an example, verbal description of me. If I were to say, Dr. Hand's children and my husband were to say Pastor Jeff's children, we would be talking about the same set of children, right? Equal sets. This is another definition of set equality that you can use. And what it actually says is that if A and B are sets, A is equal to B, if A is a subset of B, and B is a subset of A. So in other words, if I were to be able to draw this picture with A as a circle inside of B, and I would also be able to draw the circle with B as a circle inside of A, the circles must just be the same thing to begin with. And the last one on this screen talks about proper subset. So proper subset says we have a subset. It's important, you got to have a subset first. Okay, we've got a subset. A is a subset of B. And A is not equal to B. Now this is distinctly something not equal. And when that happens, notationally, you see that line that's on the bottom disappear. Kind of like when we say something's less than compared to less than or equal to. If we take that bottom line off, they cannot be equal to. And what it really means is that picture I drew at the beginning is a true picture. There's sort of nothing in the donut region out here. This piece right here, if I had a proper subset, has something in it. Right? There's actually something in it. It's not empty. That's what a proper subset means. So a really good example of this, so my brother-in-law has a daughter from his first marriage, and then he has 3 children with his wife now. They have 3 children. So if my sister-in-law were to describe her biological children, that is a proper subset of my brother-in-law's biological children, because he has 1 extra, right? She'd be in that orange region around there, and then the children that they both have in common biologically would be the middle part of the picture. Okay, so it's a proper subset idea. There's something in the orange region. All right, so I think, oops, let me see my paper. We're going to do an example next. Yeah. So what we're going to do next is we're going to actually do an example where we have the ability to choose what goes in the blank. So we have 2 sets on either side. And what we're trying to decide is whether or not we can put the proper subset symbol, the subset symbol, or both symbols between them. Or neither. Sorry, there's a 4 option, or neither. That just doesn't fit. So when you see this on my math lab, it's going to look like a multiple choice question. Multiple choice questions mean that I don't give partial credit because you have to pick one of them. And you have multiple attempts, so if you pick the wrong one, you need to repick it. Make sure you know why, because otherwise you're just going to pick the wrong one potentially the next time too, right? So we have 2 sets on number 3. The first set on the left is the elements B, C, and D. The second set on the right is the elements B, C, D, and F. And what we're going to do is we're kind of just going to go down this list. So is this, we'll start with the one in the middle here. Is this a subset? Is everything in the set on the left also in the set on the right? Yes, it is. So I could definitely put the subset symbol, the one that I've circled in that orangey kind of color, between there. Okay? So I definitely can put that one there. The question is, whether I can put the other one there too. Because if I can put the other one there too, I need to put the word both in between instead. So this one definitely fits there. It just may not be the only one. Is it a proper subset? Well, to be a proper subset means it's a subset, which it already is, so we're good with that. And it's not equal to. Is it equal to it or is it not equal to it? It's not equal to it, which means it is a proper subset. So the symbol or this symbol both fit in that blank, which means what actually goes in the blank is the word both. So both of these fit. I'll delete them because I don't want you to think that we could just put any of the 3 in. It's the word both. The word both goes in between there. Both fit in that blank. We're going to do the same thing for number 4. Take a look at all the items in the first set and compare them to all the items in the second set. Is everything in the left also in the right? Yes. So what that means is it's a subset, like this. Is it smaller? No. It's actually equal to this time. So if I had an option to put the word equal in between there, that would actually work. It's just not one of my 4 choices of multiple choice, right? I don't have that option, which means that the only thing I can put in between there that would work of the 4 choices I'm given is this one, because the other option with without the line underneath actually doesn't work. How about number 5? Is everything in the set on the left also in the set on the right? No, that's actually the easiest option, because when that happens, the answer must be neither, right? It doesn't fit. It gets ruled out immediately, and it's barely big enough for me to write it, but it's neither. Okay, is that good? Okay, the idea of subsets. There's lots of subsets given any set. So the next thing we're going to look at is actually how we decide how many subsets there are. So if we have a set with n elements, there are 2 to the power n subsets. So I'm going to write one out that's really small just so you can see what I mean by this. Let's say that we had a set A, and it has just the numbers 1, 2, 3 in it, okay? 1, 2, and 3. So there are 2 subsets that you always get for free whenever you're working with a set. You get the subset, so these, I'm going to list out all my subsets now. You get the subset that's the whole set, and you get the subset that's the empty set. Those are guaranteed always 2 of your subsets, okay? Everything else has to be a proper subset. Okay, so one of our subsets is going to be the element 1 as a set. Another one would be the element 2 as a set, and the third one would be then the element 3 as a set. That's a 3. Those are all subsets, because everything so far that I've written down, these 5 sets, are items, right? They have items in them that are in the set I started with. Okay? But I don't just have to do elements that have, or sets that have 1 element. I could have 2 elements as well, right? So I could have the set with 1 and 2, the set with 2 and 3, or the set with 1 and 3. And that's all the ways that I could group 2 items together uniquely without repeating something. So let's count. How many did I have in my list? I have 8. So let me move this up here for just a second. There are 8 of these, right? How many items are in my original set? We learned this cardinality last time, n of a. How many items are in a? 3. So this formula says I should be able to take the number 2, raise it to the number of items in my set, which is 3. And what is 2 cubed? 8. And this is just an example of this working. And it's going to work every single time. But if you had to write them out every single time, those lists would get very long very quickly. It was pretty nice for 3 elements. Once you get to 4 elements, you've got 16 different subsets to write out. And if you have 5 elements, it's going to be even bigger, right? Okay, so of these sets that we listed, some of them are proper subsets. In fact, all of them are proper subsets except for the original set itself. So if I were to count all of these, this one's a proper subset, this one, and 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 this one, all but one. The one that's everything, right? So how many of them are there? Well, there were 8 to begin with, so there's 7 proper subsets. It's just one fewer. So when we have proper subsets, we just take 1 away from the subsets. So when you do this for my math lab, it'll ask you a question, and they'll ask both questions in tandem, right? So if you miss the first one, you're going to miss the second one automatically. And I understand that because you're just going to subtract 1. So if you got the answer 42, and that's wrong, you're going to get them both wrong because one's going to say 42, one's going to say 41. So on your quizzes and on your tests, this is one of those places where I go back in and you get credit for the second one if you did it right based on your incorrect answer for the first one. All right, so just rest assured that that will be fixed. It's just that my math lab won't do it for you. I'll have to do it manually afterwards. Okay? All right, so we're going to take an example. Our example is going to have letters in it now, so there's nothing special about the numbers we've been using before. Part A is we're going to find the number of subsets, and part B is the number of proper subsets. And all of this hinges on the number of elements. So the first step in doing this is to count how many elements are in my set. So how many elements are in this set A? 5. So finding the number of subsets means I will do 2 to the power 5. You're welcome to grab a calculator. You're welcome to multiply it out by hand. Maybe you can look at this and you just know what it is. I don't care. Any of those options is fine with me. What is 2 to the power of 5? It's 32. Okay. Well, I strongly encourage you to have a calculator with you when you're doing your homework, taking your quiz, taking your test. There is one built inside of my math lab if you've played with it already. There's a scientific calculator built into it, so you're welcome to use that as you are working. So part B says the number of proper subsets. So if there's 32 subsets, how many proper subsets are there? 31. That one comes real quick. Yeah? All right, how about this one? This one wants us to look at the odd integers between -9 and 4. So it might be helpful actually to list them. And it does say between, and between means in between, which means you don't include the endpoints. Now 4 doesn't matter because it's not odd anyway. But -9's odd, and you need to know we're not including -9. Make sense? So we're going to list them out as a way of thinking through this. What would be the first one if I was starting with the smallest value? Yep, -7. Let's keep going.
-5, -3,
All right, we got them. Good. And this is called set B. So what is the number of items in my set B that you've listed? 6. So when we're finding the number of subsets, which is part A, what am I going to do? 2 to the 6th. What is 2 to the 6th? It is 64. So what is my number of proper subsets? 63. Any questions?